Hello, class. This is the physics class for Monday, December 12th. I unfortunately did not hit the record button during today's class, so I'm going to give you guys an abbreviated version of what I talked about in class. Probably even better because I won't be rambling quite as much. So today we ended up talking about Newton's second law. Last week we talked about Newton's first and third laws. Those were much more conceptual in nature, right? First law, that there is such a thing called inertia, right? A force in motion, an object in motion tends to stay in motion. An object in rest tends to stay at rest unless acted upon by an outside force. That's really just giving us that concept of inertia. There's this resistance to changing velocity. And we call that mass. It ends up being mass. One of the interesting things is that it's this mass that we're talking about here, this inertial mass, ends up being exactly the same mass that is used when we talk about gravity. Now, we're so used to doing it, we don't even give it a second thought. But if you do take a moment and think about it, these are two very fundamentally different things, or at least they seem to be fundamentally different. The resistance to motion and the attraction due to gravity. But we can find out long down the line with lots more math that there's a reason why those are connected, and it's not so obvious. But anyways, we're used to the two being together. So what happens to an object when the net force on it is zero? We learned that from Newton's first law. If there's no net force, it wants to stay moving the way it's moving, either standing still or moving at the same velocity with the same magnitude and same direction. But what happens if the force is not zero? So even last week, we were working with force table problems, and we were balancing the forces. So we made sure that the calculated force was the same. It was equal and opposite to balance everything out, so there was no net force. Now that we're moving on to Newton's second law, we're going to talk about things when there is a not, when our net force is not zero. Not zero. And this gets where things get pretty interesting. We can end up a lot of fun, a lot of interesting calculations, and very powerful just using the simple idea of F equals ma. So we call this the result of this net force in an object. We have a term for it, and hopefully you guys will recognize this term. We call this term acceleration. Let me get this typed in there. Acceleration. And how large is this acceleration? And really here it depends on two things. So I want to approach this much as more as a conceptual process this time around, as opposed to a math process. And then we'll bring the math in on the backside. So I want you to think for a moment, what if we had a force, right? And if we increase that force, then what's going to happen to our acceleration? Right, so I'm going to say F increases, then I'm going to use this arrow to being what happens to our acceleration. Well, hopefully you're going to say, well, geez, Dr. Yates, if you increase the force on something, you're going to accelerate faster. At least I hope that's what you could come up with. And hopefully it makes sense. It should be intuitive to us because that's what our normal experience is. So I'm going to replace my question mark here with increases. And we can ask a similar kind of question. Well, let's say, so we know force increases, acceleration increases. We can look at several different things, right? If we change the shape of an object, does that change how its force and its acceleration are related? Well, not really. It may seem a bit like especially when we talk about something falling and there's air resistance. Yeah, we change the shape of it and the air resistance increases. But the net force and the net acceleration, that relationship still holds true. So we can talk about what are the things that are related, and we could do experiments about it. Just changing. What can we do to impact our acceleration? And we'll pretty quickly come to another intuitive one. What happens when you increase your mass? So the example I used today in class is what happens if we went out into the parking lot here and we found somebody that has a Mini or a smart car, and we asked them if they could put it neutral for us, and then we'd select one student, have that student try to push that car, get it rolling across the parking lot. And then we would go out and we'd find some student that has a big honking SUV, and that's the same thing. Can we put it in neutral? Can we try pushing it a little bit across the parking lot? We'd pick out the same students so we know we're using the same force. And what we'd quickly see and what we'd intuitively expect, that the heavier car, the more massive car, our student can't accelerate it anywhere near as fast. Right. So what we're saying here is as we increase our mass, what happens to our acceleration? Our acceleration decreases with the same force. Right? Same person pushing it, they can't accelerate the heavier car as fast. Mass increased, acceleration decreased. So how do we put these two together, these two observations together? Right? Put those two observations together. Well, the first thing we need to do is think about, what does it mean? How do we, in a mathematical way, say that if F increases, acceleration increases? And what we would say, typically what we would say here, is that our force, acceleration, is directly proportional. Acceleration is directly proportional to the net force. Let's think about that a moment. If the force is zero, we're not going to have any acceleration. And we know that if we have a little bit of force, we have a little bit of acceleration. We have more force, we have more acceleration. So there's a relationship there. They both increase together. How about, though, mass, right? Mass. We talked about if it's the other way around. Acceleration is inversely proportional to mass. That's just kind of using words to, again, to say what we just talked about there. As a force increases, acceleration increases. As mass increases, acceleration decreases. So they are inversely proportional to each other. And had we been together and been able to do a lab, we would have done a couple things along those lines. We would have changed the force, and we would have been able to see how the acceleration increased. We would have changed the mass. We would have seen how the acceleration decreased. And we'd find out in both that it's a nice relationship, and it's one that we already know. Hopefully, again, you've heard Newton's second law, F equals ma. Now, sometimes you might see this also written just in a slightly different form. We'd see it written as A equals F divided by M. And to be honest, I learned it the first way, F equals ma. But the more I see how things are being taught and just more the intuitive idea, I think A equals F over M is a more intuitive form for us, especially when we start talking about the forces of gravity. This will it's just easier to wrap your head when you think about it that way. So we're going to use these two equations, these two same forms of this equation, and it's going to allow us to help solve a lot of problems. We know from our unbalanced force, we have no when we had our forces balanced, there's no unbalanced forces, there's no acceleration. So now we'll study motion that happens when there is a net force, when there is no the forces aren't balanced, and there is an acceleration. But before I talk about that a little bit, I want you to note here that force is a vector equation. Force is a vector equation. And what does that mean? What does that mean? Well, hopefully it makes sense. Acceleration is a vector. We talked about that a little bit earlier, right? Acceleration is a magnitude and a direction. So acceleration is a vector. Force is a vector, right? Because we can push something forward, we can push something backwards. So we already know that force and acceleration are vectors. What do we know about mass? Right? So we know that force, acceleration, and force are vectors. But what about mass? Does mass have a direction? No. Mass is a scalar. No direction. You weigh 10 grams. It's not like you weigh 10 grams north. Now, we don't talk about it that way because it's really not the way it works. So it's a vector equation. Well, what's important about that is that means we can break this down into two components. We can break it down into an x component, and we can break it down into a y component. And really the key thing here is that force, the net force, and the acceleration have the same direction. Let me move this one here out a little bit because that's getting in the way. Have the same direction. Again, might seem kind of obvious, but let's just make sure we're all understanding some of the key points. They have the same direction. So, excuse me, if we look at this based on this, we know we're going to define the unit of force as being a Newton. A Newton. So what would a Newton look like? What would its component of units be? And let's look at this. What are the units? If we take mass times acceleration, right? What do we measure mass in? Typically, we measure mass in grams, but for some reason, and I don't know why, when we talk about mass and force equations, we're actually going to be measuring it in kilograms. What do we measure acceleration in? We measure acceleration in meters per second squared. Okay. So if we look at what the units are for a Newton, it's kilogram meters per second squared. So a Newton is kilogram. I don't want to do this. Kilogram meter per second squared. Okay. Meter per second squared. Now, the reason I'm mentioning that is because when we're doing some of our problems, we have to make sure we have the right units, the right definition of our units. So when we do our calculations, we need to make sure all the masses are put into kilograms, or we're going to end up with the wrong dimensionality, we'll be off by a factor of 10 or 1,000, depending on what we've done. So how can we say this in a different way, defining a Newton? We can define a Newton. A Newton is the amount of force needed to accelerate a 1 kilogram object at 1 meter per second squared. So quick definition of our Newton. All right, so this is all just F equals ma. We're talking about being a vector equation, so our force and our acceleration have the same direction. And let's go back and apply this a little bit. And we talked about Newton's third law last week. And what does the Newton's third law say about the gravitational force exerted by you on the Earth? And Newton's law told us, right, that for every action, there's an equal and opposite reaction. So what does it tell us here? It's the same as the force, the Earth. What can you say about the gravitational force exerted on you by the Earth? Same as the force exerted by you on the Earth. Right? Just simply equal and opposite forces. They're pairs. So let's use Newton's law a little bit and kind of apply it to this situation. Right? We're used to looking at the gravitational force. We know the gravitational force exerted on the Earth or us. We've used this calculation a lot. F equals mg. Force of gravity is our mass times gravity. Well, let's just pick a nice mass here. Let's make things a little bit simple. Let's say we have a 100 kilogram person. I'll talk about the size of a good sized football player. And we know that the acceleration due to gravity, we're going to use nice numbers for that too. We'll use 10 meters per second squared for our acceleration due to gravity. Right, so what would our gravitational force be on our football player here? We're going to say 1,000 newtons. 100 times 10, it's 1,000, and we call kilogram meters per second newtons. So that's the gravitational force the Earth exerts on us. All right, if now let's take this a little bit farther. If this was the only force acting on us, so we're in free fall, that's what we use that to mean we're in free fall. The only force acting on us is gravity. What would our acceleration be? In other words, so the only force is the force of gravity. Well, if you look at our equation, F gravity is equal to mass times gravity. Our acceleration is simply what we put in for gravity, right? It's simply 10 meters per second squared. Negative 10, let's put that in there, because acceleration, gravity do have a direction, and it's down, so we do typically call down the negative direction. So let's take a look at it this way around. Let's look at the gravitational force exerted by us on the Earth. Well, Newton's third law tells us it's going to be equal and opposite. So instead of that force, and I probably should have put a negative sign way back up here because gravity is pulling us down. So let me put the negative sign in there. What's the force exerted by us on Earth? It's going to be equal and opposite. Right? So that force is going to be a positive 1,000 newtons. That force is going to be a positive 1,000 newtons. Same magnitude, 1,000, but in the opposite direction. It's in the positive direction. Now, if this was the only force acting on Earth, what would its acceleration be? So we're kind of asking again the similar question we asked about us up above here. Well, let's plug in our numbers, right? So what the Earth's acceleration, it's going to be equal to the force that we have applied to it and divided by mass. Well, let's go ahead and do that. We know that our force is 1,000 newtons. And let's go ahead and divide it by the mass of the Earth. That's what's accelerating here, the Earth. So we better use the mass of the Earth. And, geez, I can't remember what that number is. I think it was something like 6 times 10 to the 24th kilograms, I think. So let's put that in here. The thing I want you to see is the mass of the Earth is huge, absolutely huge. So when we go ahead and we try to figure out this acceleration due to the Earth, it's essentially zero. Right? That's such a small number. Let me spell, right? There we go. It's essentially zero. So again, equal and opposite forces, but because the masses are so different, the Earth hardly has any acceleration at all. That's why it works very well from our perspective. We're used to us falling to the Earth. We're not used to the Earth rising up to meet us. All right, and we started doing a few problems today, and I will do the first one here with you very quickly, and then we'll call it a day because it's just applying this in a couple different ways. I'll do the first one and the fourth one, I think. So I want you to do this the same way we've done our other problems. I want you to write down, what do we know? What are our variables that we're looking for? F, M, and A. What does the problem give us? It tells us that our force is 390 newtons to the north. It tells us that our mass is 270 kilograms. So what is our acceleration? Well, if we use our formula, A is equal to F divided by M, and we're going to see our force is 390 newtons north. And we're going to divide that by 270 kilograms. And let's see, let's punch that into the calculator very quickly here. 390 divided by 270. 1.6, well, 390 divided by 270. Did a little typo there. 1.4. 0.4 meters per second squared. And we also know it's in the same direction as the force, so we know that this is going to be north. Okay. Easy peasy, just plug in our equation. So let's go ahead and let's look at problem number 3. And the reason I like problem number 3 here is when you look at it, we've got 2 forces. The forces, it's plural. We've got one force, it's 390 to the west. We have another force, it's 190 newtons to the east. So when we go over to calculate what our forces are here, we got to be very careful. Our force, our net force, is equal to what? 390 newtons to the west. Well, usually we assume that the west is a negative direction. So I'm going to put negative 390 newtons. East is positive, so I'm going to add to that 190 newtons. And what's our net force? Negative 200 newtons. I encourage you to not use east and west like the problem does, because I find that it's going to make it harder to keep your directions straight. If you go right ahead at the beginning and convert that into positive and negative, east being positive, west being negative, then your negative signs, you carry them through, they're gonna all come out to the end and help you know which direction you're talking about. You get a positive number, you know you're headed to the east. You get a negative number, you know you're headed to the west. So I encourage you to do that conversion right away, so that you're defining yourself with respect to the positive x-axis. In this case, west would be negative. We also tells us our mass of our boat is 270 kilograms, and it asks us for our acceleration, and we've got to do the same kind of thing. So what's our acceleration? A is equal to F divided by M. Is equal to negative 200 newtons divided by 270 kilograms. And this time we get an answer, 200 divided by 270.74. Meters per second squared. And which direction are we going? Well, I dropped my negative sign there, so I'm sorry I made that mistake. We've got a negative 0.74 meters per second squared. That means we're heading to the west. Now, I'm not going to put west in here, because if I put west, I'd have to drop the negative sign, because it'd be kind of redundant or kind of cancel each other out. So I'm just going to say, if I don't put a direction on here, then we're going to assume that when you see the negative sign, then we know we're talking west. Okay. Let's see. Did I do the fourth one here? Fourth one's a good one here too. This is our first one where we have an unbalanced force. We have an unbalanced force. So what do I mean by that? Let's go ahead and let's draw our little free body diagram here. So I'm going to put a little square in here. And onto that square, I'm going to put an arrow. So we're going to have one arrow up. That's our tension. Whoop, that didn't work quite the way I wanted it to. We're going to have one arrow going up. That's our tension force. And we're going to have another arrow going down. That's going to be our gravitational force. Remember, there still is a gravitational force here. Don't ignore that. There's no normal force because there's a rope holding it up. So let's go ahead and put in our values. So I'm going to put F, and then let's make this a little t. What's our tensional force? It's going to be 21 newtons up. How about a gravitational force? The gravitational force work out to be, get it to move. Gravity. Got to figure out what our F gravity is. We got to multiply our mass by our acceleration due to gravity. What's our mass here? 4.0 kilograms. What's our acceleration? We know gravity is 10 meters per second down, but if you look at already, we've already got our arrow pointed as down, so we just need to add our magnitude here. So we're just going to multiply this by 10 meters per second squared. And what's that going to give us? That's going to give us a magnitude or force of 40 newtons. That force is down, the direction of our arrow. So we go over here to enter in our forces for do our calculation. We know our force. What's our net force? It's 21 up. Newtons minus our 40 newtons down. And we're going to end up with a negative 19 newtons. So we have a net force of negative 19 newtons, or 19 newtons in the downward direction. What's our mass? Our mass is 4 kilograms. What's our acceleration? Again, Newton tells us our acceleration, A, is equal to F divided by M. Our acceleration here. So our force is negative 19. We're going to divide that by our 4 kilograms. And we're going to equal a negative 4.75 meters per second squared. Okay. So we're accelerating down. Our string is not enough to keep us from accelerating down, right? It's not pulling up as strong as gravity is, but it's slowing us down. We're not falling as fast as we would if we had no gravity. So I'll end it there because I want you to start seeing, here's our first attempt of looking at a free body diagram where the forces are unbalanced, and we're trying to calculate what the acceleration is based on the net force. We'll pick up there tomorrow. Thanks a lot, guys. Have a good one. Take care.